Hi everyone, and welcome back. In this video we are going to discuss Coulomb's law, picking up on our previous discussion about electric charges and lightning and static electricity and that sort of thing. Here we are going to answer the question, how much force is involved when charges interact with each other? So back in 1785, Charles Coulomb kicked this off by showing experimentally that electrical force is proportional to the size of the charges involved. In other words, when he gave objects more charge, that resulted in a proportionally bigger force. And that if he changed the distance between the charged objects, a bigger force resulted if you got them closer together, and a smaller force if you got them farther away. In fact, experimentally, upon performing a set of detailed experiments and then graphing the results, a linearized plot showed that this force was a 1 over distance squared force law. So this can be summarized by saying that the force between the objects is proportional to the product of the charges, product of the magnitudes of the charges, that is, and inversely proportional to the square of the separation distance between the charges. Now these subscripts denote the individual charges. For example, Q1 and Q2 is like, okay, charge 1 and charge 2. So two different charges. R12 simply represents the distance between the centers of charge 1 and charge 2. Now, this proportionality symbol tells us, okay, the force is proportional to this, but it doesn't tell us what the actual force is. Well, the actual force was found by experiment, or at least the proportionality constant was found by experiment, and if you put charges in the charge units in coulombs and the distance units in meters and the force units in newtons, it is found that the proportionality constant is K, which is called Coulomb's constant, and it's about 9 times 10 to the 9 Newton meters squared per Coulomb squared. Now notice those units. We need units of newtons on the left side, so you don't see any newtons over here in these quantities, so that needs to come out of the units of the constant. You do see a distance squared in the denominator, so we need to cancel that out with meters squared in the numerator. And you see units of Coulomb squared in the numerator, so we need to cancel that out with Coulomb squared in the denominator. So using that little bit of dimensional analysis, we get that our units for K are Newton meters squared per Coulomb squared. You can express them in other ways as well by breaking down what a Newton is, setting a Coulomb as like an amp second, that sort of thing. But in any case, I should mention that in many cases you will see this Coulomb constant K written as 1 over 4 pi epsilon naught. And the reason we often do that is because there are many applications involving this equation, especially once you scale it by a charge factor to talk about electric fields, where you get factors of 4 pi running all over the place. So it's like, okay, a lot of times it just makes more sense to speak in terms of this epsilon naught and cancel that factor of 4 pi that often occurs. This will occur all over the place in Gauss's law problems especially. But in any case, epsilon naught, which is just 1 over 4 pi k, we call it the permittivity of free space, is about 8.854 times 10 to the minus 12, notice the units, Coulomb squared per Newton meter squared. Oh, those are the inverse units of K. Well, they'd better be, because epsilon naught is 1 over 4 pi K, and 4 doesn't have units and pi doesn't have units. Now, does this equation look familiar? Well, it really should, because it's basically Newton's law of universal gravitation, except with charges instead of masses, and a different proportionality constant. But Newton's law of universal gravitation has the exact same form. It's an inverse square law. It talks about a force between two objects having a certain property, which in that case is mass. In fact, this type of situation will occur whenever you have a force law where the force is spherically symmetric. In other words, it appears the same any way you look at it, and it propagates outward in all directions. So you're going to get an inverse square law in that sort of situation. This will make a lot more sense when we talk about electric fields later on in this unit. So I've just told you the magnitude between for the force between two charges. But keep in mind, remember back from kindergarten physics, force is a vector, which means it has a magnitude and a direction. And in a lot of cases, the vector nature will become very important. But before we get to that, let's look at a typical example that you might get for a type of problem that you might be asked to solve for homework. So you've invented an electron pump that moves electrons from one object to another, and in demonstrating this invention you bolt a small metal plate to the ceiling and connect the pump between the metal plate and yourself, and then start pumping electrons from the metal plate to you. So the question is, how many electrons must be moved from the metal plate to you in order for you to hang suspended in the air 2 meters below the ceiling if your mass is 60 kilograms, which is about 132 pounds. So let's look not just only at the solution, but emphasize the steps that you need to go through in order to get credit for showing your work in these types of problems, such as in homework checks, tests, AP exams, and such. So we list our givens first. Sometimes they'll even give a point for this every once in a while. So listing givens in a problem is just good procedure in terms of solving our problems. So going back to the problem, we have a mass of 60 kilograms that's going to be lifted. There's going to be a distance of 2 meters, which we're approximating as the distance, so to speak, even though, of course, the charges will be spread around evenly. And we have a number of charges that get moved. Well, they're asking how many electrons. So it's like, okay, n equals question mark. We wrote down our distance, we wrote down the mass. Well, we want to use Coulomb's law for this. So F equals K Q1 Q2 over R squared. But what is the Q? Q is the amount of charge on me and the amount of charge on the conducting plate. Well, how much charge is that? Well, we've said that we're moving a number of electrons from the conducting plate to me. So a number of electrons going from one to the other. Well, in terms of a force magnitude, it's an attractive force because we're moving electrons from one object, putting them on the other, so the object they're getting moved from will be positive, the object they're getting moved to will be negative. Well, how much charge is that? Well, the amount of charge that's accumulating on me is equal to the number of electrons that I get times the magnitude of the electron's charge. So that's, you can call that Q1, but that's the same as the amount of charge that's getting removed from the conducting plate. We're going to call that Q2. And whether we call it Q1, Q2, either way, it doesn't really matter. The point is that the magnitudes of those charges are the same. So since a certain number n of electrons are moving to me, and the magnitude of the electron's charge is lowercase e, which is the elementary charge, that's the amount of charge that I have. And that's also the magnitude of the charge that's on the conducting plate. Now, I should note that lowercase e, the elementary charge, is about 1.6 times 10 to the minus 19 coulombs. Is that a number you should memorize right now? No. Is it a number that you will memorize by the end of this course? Yes, not because I'm going to force you to, but simply because you're going to do so many problems that end up using that number, it's just going to become second nature. But anyway, we draw a free body diagram here. It's always a good idea when you're doing problems involving forces. So you have an electric force upward preventing you from falling in this situation. Remember, you're getting elevated 2 meters off of the ground, and a force of gravity called your weight downward, W equals mg. So there's our free body diagram. So how do we solve problems like this? We go back to Newton's second law. Newton's second law says the net force on an object is equal to that object's mass times its acceleration. Cause and effect, like the acceleration of an object is equal to the net force, the cause, divided by the mass, the acceleration being the effect. Well, what is the net force? F equals ma. Well, the net force comes from our free body diagram. We have an electric force up is positive, minus a force of gravity, the weight, down. So there's where the minus sign comes from. F sub e minus w. equals 0. Why is it equal to 0? Well, because we're told that we are suspended above the ground. Suspended means we're just hanging there. We're not accelerating. So the acceleration is 0, which means, therefore, the net force must have been 0 by Newton's second law. So we have, or really you could say Newton's first law as well, because Newton's first law says that objects have 0 acceleration in the absence of a net force. So, well, there are forces here. The net force, therefore, is 0. So F sub E up minus weight down is 0. So that means that the electric force is equal to the weight, just solving this equation. Well, I know of an equation for electric force. We just talked about it. That's Coulomb's law, kq1 q2 over r squared. I know an equation from weight. I learned that back in kindergarten physics, W equals mg. So we plug that in on the right side. Now, what are these charges, though? I mean, charge isn't in our givens. N is in our givens. Well, this N ends up going into each of these charges because of one of our other givens, the fact that we realize that we're transferring a bunch of electrons, N of them, and each charge is N times E, where E is the elementary charge. So we plug each NE in for the Q's and work that out. And we're solving for n, so we isolate for n, multiply both sides by r squared, divide both sides by ke squared, and take a square root to get n by itself. And now we're ready to plug in numbers. We're going to plug in the mass of the thing that's hanging, plug in g, plug in k, those are constants, plug in e, that's a constant, and plug in how high it's hanging above the ground, that's 2 meters. So it's time to do that. We plug in our mass, we plug in g, we plug in for k, and we plug in the elementary charge. So after doing that and shoving all of these things into a calculator, we find that apparently 3.2 times 10 to the 15 electrons have been transferred in this process. That is 3.2 quadrillion electrons. In case you're curious how much charge that is, remember that the elementary charge is 1.6 times 10 to the minus 19 coulombs, so just multiply that number of coulombs by this number of elementary charges, and you find that it's just over half a millicoulomb. A millicoulomb is actually a really big amount of charge. When you're talking about doing things with Van de Graaff generators, you're usually talking about nanocoulombs or maybe fractions of microcoulombs. Let's look at another example. So in this figure, we have two tiny conducting balls of identical mass and identical charge hanging from non-conducting threads of length L. So Part A, derive a simple expression relating the separation distance x, shown at the bottom of the figure, with the other variables, assuming that that angle theta is small. And then, Part B, given those particular numbers, calculate the charge magnitude Q. Now this derive a simple expression relating variables to each other, this is a very common prompt on the free response part of the AP exam. Get used to solving for problems in terms of the given variables. Notice that's what we did in the previous example. We solved first for n in terms of given variables, r, m, g. Well, really just r and m, and then only after that did we plug in our numbers. That is generally good physics practice. You solve for your expression first in terms of variables, and then after that, if you're actually given numbers for those given variables, then you plug in the numbers. So something to keep in mind, that's what we're going to be doing here. So we're trying to solve for that distance x. Well, free body diagram time. Let's look at one charge in particular. How about, say, the one on the right? Well, the one on the right, it certainly feels a force downward. That's why it's hanging to begin with. That's its weight, W equals mg. Why is it deflected off toward the right? Well, it's deflected off toward the right because of this electrical force from this other charge. I'm going to call that F sub E. Why doesn't the thing end up just falling and accelerating off toward the right due to gravity and the electric force? Well, because it's hanging by a thread. No pun intended. The tension is that force, so we give it a name. We're going to call it capital T. And there we go. That's our free body diagram for one of the charges. Well, we're going to set this up two different ways. First, we note that the net force in the y direction is 0. Newton's second law is a vector force law. F vector equals ma vector, which means that the vector components are also equal. In other words, F in any direction is equal to m times a in that same direction. Well, here, two very convenient directions are what we normally think of as the Cartesian x and y directions. So in the y direction, the vertical direction, which we're going to call y, net force in the vertical direction equals mass times vertical acceleration. Well, it's hanging, so that acceleration is 0. Well, what is the net force in the vertical direction? We need to decompose one of our vectors into horizontal and vertical components. The other two already are decomposed. The tension is diagonal. We need to decompose that into horizontal and vertical components. So that tension, well, what about F sub y? The y component, the vertical component of that tension, well, given these angles theta that are in this diagram, that would also be the same, by opposite interior angle theorem, as the angle between the vertical and the line here. So in other words, the vertical component of t is going to be t cosine theta. So we have t cosine theta for our vertical component of tension. And, well, are there any other forces in the vertical direction? Aha, we have the force of gravity, the weight in the vertical direction. So we have t sub y minus w equals 0, and that translates into t cosine theta minus mg equals 0. Well, that means t cosine theta is mg. And from that, we could actually solve for t. But we don't need to solve for t. We're trying to figure out what that x is. Well, what about in the x direction? We have the net force in the x direction is equal to mass times acceleration in the x direction, which is also 0 because, again, it's hanging, it's not moving back and forth or anything like that. Well, what forces do we have in the x direction? We have this electric force to the right, so that shows up as a positive, and we have the x component of tension to the left, so that's going to show up as a negative. So the magnitude of the x component of tension, well, we have kind of imagined the x component of tension completing a triangle, go up and then to the left. Well, the part to the left is opposite of that angle theta, so we're going to have a minus t sine theta going off toward the left. So we have F sub e minus t sine theta equals 0. Okay, so what can we do with that? So we know the equation for electric force. It's kq1 q2 over r squared. The q's are the same. They're just called q. The charges are the same, that is. The r, the distance between the centers of the charges, is called x in this picture. So just from looking at one of the charges, we can figure out what's going on in the interaction between both of the charges. Okay, so what does that mean? We can actually get rid of these tensions by dividing the bottom equation by the top equation, because t sine theta divided by t cosine theta is simply called tangent theta. The tensions cancel. So tangent theta must be the left side of the bottom equation divided by the right side of the top equation. In other words, I kind of flipped one of the equations to begin with to get t sine theta on the left side. So anyway, we have kq squared over x squared over mg. So that translates into what we have here. Now, if they gave us this hint that the angle was small. If the angle is small, we can say that tan theta is approximately equal to sine of theta. And they want this in terms of given variables. Like, in other words, we have this string length L. So since we have tan theta is about sine theta, well, what is sine? Sine is opposite over hypotenuse. Well, opposite of this angle theta is going to be half of this length L, or sorry, half of this length x. That's called x over 2. So we have x over 2 opposite over hypotenuse, L. So x over 2 over L, which is just x over 2L. that is sine theta, so we're going to plug that in for sine theta, and we're plugging sine theta in for tan theta. So now that we have that, having plugged in sine theta for tan theta and x over 2L in for sine theta, the right side is still kq squared over mgx squared. Well, because of the fact that we made that approximation and we didn't have really nasty square roots coming in, we were able to get all of our x's by themselves without having to solve nasty equations that you get tortured by in your nightmares. So we get x cubed on the left, multiplied both sides by x squared, multiply both sides by 2L, and then you get x cubed equals 2kq squared L over mg. Solve for x by taking the cube root of both sides, and you get x equals cube root of 2kq squared L over mg. And now we're ready to plug in our givens, which we write down like good physics students. So we're being asked to solve for the charge q. Sorry, I was mistaken early on. I said we were asked to solve for distance x, but we're asked to solve for the charge q. So we do that. And now we plug in our numbers. So there's our equation for q. Q equals square root of mgx cubed over 2kl. And now we plug in our numbers to get the charge q, which is 3.1771 times 10 to the minus 8 coulombs. That is about 32 nanocoulombs, or 31.8 nanocoulombs. So that is how you can solve problems like this. Note the approximations that we made. We could have said, oh, well, if theta is small, then sine theta is just about equal to theta. But that wouldn't have actually helped us. We actually needed sine theta in order to make the problem work out. So that's the end of our discussion about using Coulomb's law to solve for unknown variables in problems like this. In our next discussions, we will look at how to use Coulomb's law to figure out net forces on charges that are arranged in a straight line in just one dimension, and then the net force on charges that are in 2 dimensions. So that will be the subject of our next videos. Thank you for watching, and if you have any questions, please put them in the YouTube comments. Thank you.